Great. So let's go with the Carnot cycle right now. So this Carnot cycle is also called as the Carnot ideal heat engine cycle. So actually there are four phases in the Carnot cycle. They call it the isothermal expansion, the adiabatic expansion, isothermal compression, adiabatic compression. There are a couple of entities over here which we have to understand. Step one, we are going to have a cylinder in which the working substance is housed. This cylinder which we are looking at is going to have insulating walls. There's going to be a frictionless piston internally, and there's going to be a conductive bottom or conducting base. The working substance is inside. It can be a liquid or it can be a gas. We are going to have a source which is placed at a temperature T1 Kelvin, which is a very high temperature. We are going to have an insulating pad whose use you'll understand in a minute. And we are going to have a sink which is placed at a temperature T2 Kelvin. Now we have to clearly, let's at the same time also plot a graph as well. Let's take volume and let's take pressure in this fashion. Pardon me. Yeah. So let's start with the process. First, this working substance or this cylinder containing the working substance is housed on top of the sink. So the moment we keep the working substance on top of the sink, what actually happens? Heat energy flows from the sink into the working substance. Now we have to understand that there is actually at the same time weights on top of the working substance as well. So when it is kept in the first case on top of the sink, the weights are slowly removed in infinitesimally small steps as well. So what happens? Slowly the volume of this particular working substance begins to increase, and we know by Boyle's law the pressure is also supposed to decrease. There is a temperature which is also being given, that is the heat energy being conveyed to the working substance. The significance of which is that whatever heat energy is being conveyed to this working substance is used by the working substances, that is, it's used by the system in order to increase its own volume. In other words, there are two factors here. One factor is actually defined as expansion, which everybody will agree with. And the other factor is actually isothermalism. Why is it isothermal? Because the net temperature of this particular two entities will remain, this temperature is going to remain constant. Or in other words, the temperature of the working substance, the temperature of the system is going to remain constant. Why? You supply some amount of heat energy, that same heat energy is actually used by the working substance to bring about an increase in its volume. So I can combine the two factors and say the first process is actually isothermal expansion. Secondly, this has been done. So the working substance is now at a particular temperature. Now we place on top of the insulating pad or the insulating stand. When we do so, and again the weights are removed slowly, infinitely small steps one by one, we have to know that there is no transfer of heat energy between the working substance and the insulating pad. Or in other words, to comply with the definition of an adiabatic process, there is no transfer of heat energy between the system and the surroundings. Because although we have a conducting base over here, we have an insulating pad which is entirely insulated. As a result, we have no transfer of heat energy between the two, so it's an adiabatic process. But at the same time, weights are removed, which means expansion is taking place, right? Weights are slowly removed, so the pressure also decreases in accordance with Boyle's law, which therefore means I have an expansion taking place adiabatically. So the second phase is defined as adiabatic expansion, correct? Adiabatic expansion. So let us plot these two phases on the graph, most importantly. So we have a particular point. Let's say it starts at pressure at A, the temperature is T at A, and the volume is at A, correct? We know that as the volume increases, the pressure has to decrease. So what happens? The volume slowly goes in this fashion over here. It goes to VB. As it goes to VB, the pressure also decreases, which means PB. And the temperature remains constant because this is an isothermal expansion, so it remains T of A itself. Or let me call it in other words, instead of A, let's write it as 1, and let's write it as 1. So this part denotes isothermal expansion, or the first part. Now when we kept it on the insulating pad, what happens? We still know that there is an increase in the volume and therefore a decrease in the pressure, but the temperature of the working substance decreases. Why? No heat energy is being supplied. Whatever inherent heat energy is present in the working substance is being used up by the working substance to do some amount of, or is being used up in order to do some work to bring about an expansion. As a result, we obviously have a decrease in the volume. Or let me just make it a bit more accurate to comply with textbooks. This fashion, yes, and we are going to have a further decrease to, let us say, pressure at C, volume at C, and this time the temperature will be T2. So this is defined as the second part as the adiabatic expansion. Now when the working substance is kept on top of the sink, which is kept at T2 Kelvin, and we start to add the weights, we increase the number of pistons on top of the frictionless piston. What happens at that time? The volume of the working substance decreases. When the volume decreases, the pressure increases. When this happens, there is a certain amount of heat energy which is actually there is an increase in the internal energy of the working substance. So obviously there is a transfer of heat energy when you keep it on top of sink between the working substance and the sink. So there is heat energy being transferred from the working substance into the sink, correct? So because at the same time there is some amount of work which is also being done on the system, so whatever heat energy is being given by this working substance to the sink is compensated for a heat energy which is given to the working substance, or in other words the work done on the system, because of the addition of these weights. As a result, there is no difference in the temperature, or in other words the delta theta is equal to 0, or in other words the temperature remains constant. So isothermal process. Now the volume increases, and because the volume increases, it means what? It's a compression. So because there is a temperature remaining constant and we have a decrease in the volume, or rather a compression taking place, we have the third important phase called as the isothermal compression. Now take the working substance. So let us call the third phase as isothermal compression. Great. Take the working substance, place it on top of the insulating pad. When you place it on top of the insulating pad, again it's adiabatic because there is no transfer of heat energy between the body and the surrounding, between the working substance and the insulating pad. So as a result, at the same time, the number of cylinders kept on top of the frictionless piston increases, which means the net work is actually in temperature is actually, there is a difference in the temperature. So what happens? There is no transfer of heat energy between the body and the surroundings, but at the same time, there is a compression taking place. Because there is a compression taking place, we define the fourth phase to be defined as, keeping in compliance with the adiabatic definition, an adiabatic compression to take place. Then the same working substance is kept on top of the sink, and the process goes on, and this is what is called as a Carnot ideal cycle. To plot the next two parts in the graph, let's take the isothermal compression, right? This part, what actually happens, both the cases there's a compression taking place, which means pressure increases and ultimately goes back to the same pressure, initial pressure, and goes back to the same volume. So I can just draw simply one graph to this fashion. So this is what is responsible for a graphical representation of the Carnot's ideal heat engine cycle. That's it.